Hello students, welcome back. Let's go to problem 3. The following observations were made on fracture toughness of base plate of 18% nickel maraging steel in KSI square root of inch. Excuse me, I have no idea what this unit means, so let me just skip that part. After all, this is not an engineering course, this is a math course, so I don't have to worry about the unit. Let's just work on the numbers. By the way, this is the source of the problem. It came from actual research. And in my original problem, I did not give you the mean and the standard deviation. I gave you only the data table, and students were expected to find out the mean and the standard deviations on their own. And if you do it right, here we go. The sample size, there were 22 observations, and the sample mean was 77.33, and the sample standard deviation is 5.037, approximately speaking, of course. Okay, we don't need any of these now. This is sufficient. See? This is sufficient. We don't need entire data table anymore. The data table was there so that you can calculate the sample mean and the sample standard deviation. Oh, of course, you can count them and get the sample size as well. But for the rest of the problem, this is sufficient. Okay, 3.1. Explain why the t-curve is more appropriate than the z-curve in this case. There are several criteria, but only one of them actually counts for 1,000 level students. That is, small sample size. And it's 22, way less than 100. Okay, that's for t. That's sufficient for me. There are other criteria, but most of the times 1,000 level students do not have to worry about the others. The original distribution is believed to be normal because it's an observation. These are all coming from observation, not sample study from a population, which may have some weird kind of skewed form. This is coming from observation, so it's clearly normal. And the standard deviation is unknown. Yes, it is coming from observation, so closer to unknowable rather than unknown. And third, the sample size is small, and as a matter of fact, this is the only one that actually counts for 1,000 level students. And these two may be some wordy topics for Math 3680 maybe, but for here in 1680, only this one actually counts. 22 is less than 100, way less than 50, or never mind, small sample size, t-curve. Alright, based upon this study, find the 99% lower confidence bound and estimate 95% confidence interval. I think I must have copied this problem from a textbook. Otherwise, most probably I must have written confidence interval problem before confidence bound problem because confidence interval problems are more important and usually makes a little bit more sense. Maybe not. In this particular case, lower confidence bound make a little bit more sense, because this is about fracture toughness. So the researcher here is going to be keenly interested in screening out a substandard product. So things are going exceptionally well is no concern for us. If this fracture toughness is extremely strong, then that's good. No problem there. Now, if it is exceptionally weak, that's a problem. So in this particular case, lower confidence bound is more important. Okay, so all right, let's go with this order. Let's find out the lower confidence bound. Here's the initial picture. We have lower confidence bound, so shading is only to the left. 99% here and 1% there. Make sense? and the center is clearly 77.33. Here I use a little bit more accurate figure. Okay, now how do you get it work with t-table? T is again n minus center over SE. Same as the Z formula, so you don't really have to memorize two formulae. T formula, Z formula, they are the same. And of course, if you draw the picture, of course, that's really clear to you because the picture is pretty much the same. Now, what's the end? You don't know. What's the center? 77.33. And then what is the standard error? What's the standard deviation? 5.037. Okay. 5.037 over square root of the sample size, 22. And that has to be equal to something. And once that something is determined, it's not going to be too difficult to find this one out. It's just an algebraic equation. So let's determine this using the t-table. Ready? Okay, let's go to the t-table, and it looks like this. We have a picture, and we have probability of the shaded region, and that's to the right. And then we have the shaded probability here, which is 0.25, 0.20, 1.5, etc., etc. And then we have the t-values, t-scores, not the probabilities. These are the probabilities. That part is the shaded part. And all these are t-scores. And then we have something new, degree of freedom. And I hope by now everybody knows what degree of freedom is n-1, and the sample size is 22. So the degree of freedom is, in this case, 21. So that's the degree of freedom. Come on, degree of freedom. And then we are looking for what? 21 here. Oh, it's so difficult to highlight. Look at 21 here. And the probability here has to be 1%, isn't it? We want 99% lower confidence bound. So yes, 1%. So I want 1%. Where's 1% right here? So I'm getting 2.518 as the t-score. Does it make sense? Degree of freedom is 22 minus 1, 21. So here in this row. And the shaded probability here is 1%. It's 2.518. So there you go. 2.518. And we are nearly done. Why not complete it on? It's nearly done because this is to the left. So from here, I have to move to the left, right? Left is negative. We need negative. In the t-table, all these are for right-hand side shading. In order to get to the left-hand side shading, you have to change the sign to negative. Okay, the algebraic equation is now done, so let's solve it. X minus 77.33 is approximately equal to negative of 2.518 times the denominator flipped over. So the standard deviation 0.3037 over square root of 22. So x is therefore approximately equal to, and then let's flip this mean to the other side, 77.33 minus 2.518 times 5.037 over square root of 22. This is a computation I have to do. This is the SE, standard deviation over square root of n, And this quantity here, 2.518, came from the t-table. Here, right here. Degree of freedom, 21, and 1%. Shaded part is 1%. Okay, let's do this computation, and that's gonna be it. 74 point something, and that is my 99% lower confidence bound. Okay. Okay, we are done with the confidence bound problem. Let's go to confidence interval problem. Now we have to do it both sides, left hand side and right hand side. And here's the initial picture, of course, 95% in the middle, 2.5% here, 2.5% there. If this had been z-table, then z-value has been 1.96, plus or minus 1.96, but no, this is a t-curve. So you have to look up the t-table and do something from there. What is the t-score? T is n minus center over SE. And that's approximately equal to, in this case, minus 77.33 over the standard deviation of 5.0, I forgot, 037 over square root of the sample size, square root of 22. So that's the quantity I'm looking for. And then if I get my t-value associated to that, that's going to be the right-hand side. Once I get it, solve an equation to get x2 is not too bad. Let's go to the table here. We have 2.5% here in the right-hand side. So from this table here, I want 2.5%, 0.025, this one, this column, and then the degree of freedom is 21. It's got to be this one. No, it's got to be this one. Sample size is 22, so 22 minus 1, we have degree of freedom of 21, and 0.025, 2.5% in the right-hand side. Also, you can start from down below, 95% confidence interval, so 95% confidence level, and then you can go up to the degree of freedom of 21. Either way, you're going to get 2.080, excuse me. So you're going to get 2.080. I already forgot. Let's get that again. Yes, that's correct. And then from here, you can find out what x2 is. Let's see, what is this quantity? 79 point something. That's the x2 value, the upper bound of the 95% confidence interval, this one. Now, what if you're looking for the lower bound, this x1, and by symmetry, this is negative, that's negative. And as for this quantity here, of course, I have to recalculate. Change the sign only, and this is what I'm getting. 75 point something. And there goes the lower bound of the confidence interval from here to there. See the conclusion? They fit.